Welcome to the 11th lecture from chapter number 7. We are studying VLSI design, and in this lecture we'll study implementation of a general CMOS schematic using given a Boolean expression. Earlier we studied that a CMOS is composed of a PMOS array and an NMOS array, where we have equal number of PMOS transistors and then NMOS transistors if you want to implement a Boolean expression, right? So in this lecture we'll follow two steps to convert any given Boolean expression into its equivalent CMOS schematic, right? The steps are here. We will be given an inverted Boolean expression, for example an expression like this, or an expression like this, somewhat like this, but it will be inverted. So we'll apply De Morgan's law repeatedly unless the inversion is completely distributed on each and every variable. We'll then ignore inversion and we'll implement using PMOS. If there are an AND operation will be resulting in series connected transistors, and OR operation will result in parallel connected transistors. Step number 2 is we'll ignore inversion in the original expression, this one, and we'll implement using NMOS, and the same will be true here. That AND operation will result in series connected transistors and OR in parallel connected transistors. So this fact will remain the same, right? So by following these two simple steps, we can implement any given Boolean expression. For example, we are given this Boolean expression. It's a 2-input NAND. We also call it NAND 2, right? So step number 1 would be we'll apply De Morgan's law. This inversion is distributed on A and B, and the operation is replaced with its dual. The dual of AND is OR, and we'll implement using PMOS. Since there is an OR operation, it will result in two parallel connected transistors, and both of them will be PMOS, right? Step number 2, that will ignore inversion in the original expression. This is the original expression. We'll ignore inversion. That will be A dot B. If we ignore inversion, that will be A dot B. So implement that using NMOS, and the same will be true if there is an AND operation. The transistor will be connected in series. So it's an AND operation. We'll have two transistors connected in series. A and B, and the output F. Right, this is how we can implement a simple Boolean expression using CMOS by following these two simple steps. The next, we can verify whether the schematic that we have implemented using CMOS fulfills the truth table of a NAND 2, a 2-input NAND. We know that for a 2-input NAND, output or F would be that if we have both 0, 0, the output, since this is the opposite of AND, this should be a 1, a 1, a 1, and a 0. Let's see whether it fulfills this truth table. Let's give these transistors names: MP1, MP2, MN1, and MN2. Right, and here we are going to write the status of these 4 transistors for every input combination applied at the input. Right. If we have 0 and 0 applied as input, since VSG would be greater than VTP, VSG for this transistor would also be greater than VTP. So these 2 transistors are on. And if we apply 0 and 0, this A and A are the same, these B and B are the same. 0 BGS for NMOS transistors will be smaller than VDN, so these 2 transistors would be off, and the output would be logic 1. VDD available at output through MP1 and MP2. Right. For the next input combination 0 and 1, if we apply a 0 here and a 1 here, this will be off, but this transistor MP2 will be on, providing a logic 1 at the output. Since this is a parallel path, if either MP1 or MP2 is on, we'll get a VDD at the output. But to get a 0 at the output, both MN1, MN2 and MN2, they both have to be on because they are connected in series. For the second combination 0, 1, this MN2 is on, but we cannot have a 0 at the output because MN1 isn't on, it's off. Right. For 1, 0, that will be the opposite of what we had at 0, 1. This transistor will be on, MP2, and the output would be logic 1. Output cannot be logic 0 because MN2 is off. Right. And for the final input combination 1 and 1, both MPs would be off because VSG is smaller than VTP, so both are off, and both MNs are on, and we'll get a 0 at the output. That fulfills the just table of 2 input NAND. Let's call it NAND 2. Right. Another simple example would be this. This is a NOR 2 input NOR. So we'll apply step number 1, that is, we'll apply De Morgan's law repeatedly, and we'll distribute this inversion on each and every variable, and then we'll implement it using PMOS transistors, and we'll ignore inversion first and then implement using PMOS transistors. And step number 2, we'll ignore inversion from the original expression, that is this one, A or B, and we'll implement it using NMOS transistors like this. So this is a CMOS implementation of a 2 input NOR. It can be extended to 3 input NOR, this can be extended to 3 input NAND, and so on. And there is a homework for students that you need to verify the truth table for NAND 2, verifying that this CMOS implementation indeed implements a NOR 2, just like we have done for NAND 2. Right, that's all for this lecture. In the lectures to come, we'll keep on studying more about DC and transient analysis of complex CMOS circuits.